Right. I want to discuss about uncertainty in measurement. Okay, so let's write it. So uncertainty in measurement. So let's think about the simplest situation. So you want to measure, uh, let's say length of your, I don't know, maybe your stick. Okay. Um, and then you want to report what is the length of the sticks. Right. So let's call the variable involved x, and x is can be regarded as random variable. Okay, in most measurement we can uh, assume that uh, the the value is normally distributed, and uh, usually we report the length of these sticks as x equal to the the mean of x plus minus the standard deviation of the sticks, okay, from the measurement. So when we write this way, okay, we are saying that 68% of so this is your standard deviation. So we say that 68% of uh, there are 68% uh, probability that the value okay, I don't know, the value that lies within x plus sigma or x minus sigma is 68% of our measurement. Okay, 68% of our measurement lies within let's say this is the mean, okay, within the mean plus sigma and mean minus sigma. Okay, uh so how do we get mean, how do we get sigma standard deviation? That is I think you can refer that to uh, to statistic, probability and statistic textbook. It's not that difficult. And now the main concern here is instead of one variable, what about if uh, your measurement involve multiple variables, and the uh, then you are required to use those variables to calculate a derived quantity. Let's say instead of stick, you are measuring uh, you are measuring a cuboid. Okay, so many cuboids. So you measure x, y. Maybe cuboid is a bit complex. Let's say area of uh, area of a area of a paper. So there are many similar paper, and you measure x and y, x and y, okay, x and y, so on and so on, and then you have to determine the area, x times y, right? So how do you uh, declare your uncertainty. Yeah. So the example can be expanded for not only two variables, three. It can be 3, 4, 5, and more variables. So uh, in in uh, in many reference, you may find uh, you may find the uncertainty, okay, written as delta r equal to partial derivative of f with respect to x, delta x, and round f round y, delta y, round f round z, delta z, so on and so on. And this is because uh, the okay, this is because let's say your derived quantity that you want to determine is r. Okay. It is function of x, y, z, and so on. Okay, if there are many, there are more than three variables involved, right? And uh, and okay, and other than this, there's also uh, you will find uh, instead of delta r, okay, for let's say I don't know, in any value, okay, let's say z equal to f x y z and so on, and then the uncertainty, okay, uncertainty of uh the uncertainty, square of uncertainty of, let's say, this function is written as round f round x square delta x square plus round f y square delta y square round f over round z square delta z square, so on and so on if you have more. So the uh, so the uncertainty of z, okay, is simply the square root of these whole terms. Okay. So this is uncertainty. This is also an uncertainty. So how we can end up with this mathematically both are valid, okay, but uh, examples shown that if uh, using the top one, if using the first approach, your uncertainty is bigger than if you use the second approach. So I want to explain how we end up with the generic, the general uh, representation of uncertainty uh, approach number approach by number one and by the number two. Okay. So for the approach number one, there can be Oh, by the way, yes. By the way, before I go further, you also may find uh, see, the data are written in this way: round f, round x, delta x. It is modulus. Y, it is modulus delta y, round f, round z, modulus delta z. So it is modulus because so the reason is because okay, so there's possibility that when you take when you do partial, when you perform partial derivative on f, you might uh, get uh, negative results. Okay. So that will make your uncertainty smaller, right? But the the way we declare uncertainty is that we want to consider uh, its largest possible. Okay? Its largest possible. So which is why uh, we make everything positive. So that's the largest possible for our uncertainty. So this also you can find it in in reference in some references. Okay. Mm, so now, so if the question here is which is better, one or three, three is definitely better because three is more conservative rather than one. Okay, and one, I'm afraid you might, if you do number one, you might have negative uncertainty. Okay, if the respected term produce the greatest value. Okay, now how can mathematically we derive number one? So there are few ways. First is using the Taylor's theorem. So I'm not going to use Taylor's to show you the Taylor's theorem here. Okay, so you can have the Taylor's uh, theorem on uh, one dependent variable function with one independent variable. And you can also have Taylor's theorem on multiple independent variable. So this one, let's say fx, or you can have fxy or fxyz, so on and so on. So if you want to know more about the Taylor's theorem, please check the calculus textbook. But I'm going to only show you uh, the results here. So let's say the z, your derived quantity that you are required to find is z, which is function of x and y. Then using the Taylor's theorem, okay, and so let's say okay, I'm going to state the results only at the final. So let's say uh okay, let's say this axis is your x value, shows your x value, this your y axis is y value, and this one is what is z, okay, because of x and y. So when you move x a little bit and y also a little bit, y no, x y plus delta y. So z actually move a little bit. Okay. And if you do Taylor's theorem, you will have the delta z. So delta z is the uncertainty. Is the uncertainty here. Okay. So delta z equal to round z over round x delta x plus round z over, oh not delta, it's round z over round y delta y plus, so this is the term if you do the Taylor's expansion. Okay, the terms inside the rest of the term is squared. Okay, it is second order derivative and squared. Okay, if you go further, then there will be third partial derivative and power of 3. So all the term can be considered as 0 because they are small. So so you so the delta z, which is the uncertainty in z, is the round z over round x plus round z over round y delta y. Okay. The second way is using is by finding the total derivative of z. Okay. So if you wants to know the increment of z, you can do the total derivative. Which is the derivative of z with respect to x delta x plus partial derivative of z with respect to y delta y. I'm not showing the details about the partial derivative. You can check that in your calculus textbook. So either way you you get what is shown as approach number 1 here. Okay, and then what about the approach number 2? So that is the simplest way to say this is by uh, squaring what you get from uh, let's give number. This is number 4. This is number 5. So you can get square of z by squaring number 4 or squaring the number 5. So when you square them, you will when you square them, you have to neglect the, let's see, let's show number 5. So if I square number 5, okay, that is round z or round x square. No, delta x plus round z over round y round y round z over round x delta x plus round z over round y delta y. So you get round z over round x square delta x square plus 2 round z over round x delta x round z over round y delta y plus round z over round y square delta y square. So you have to neglect this term. Okay, but that way is not very intuitive. Which is why we have to think about the standard deviation in normal distribution. So let's say back to the first example. Let's go back to our first example that involve the sticks. Okay, it is just single just a single independent variable. So the variance of the length is the xii to n minus the mean square over n. So it is the average of this one. We call this deviation. So how much each measurement differs from the mean value. So deviation. So standard deviation is the mean of the mean of deviation. So all deviations. The variance. So the standard deviation is square root of that. n. Okay, square root. So 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 x is mean plus minus standard deviation. So 68% of our measurement within this within this sigma, within this standard deviation. Uh, and we can and further we can rewrite xi minus mean as delta x. Okay, and we can write it this way. Okay, now when instead of one one type of measurement, okay, you have x, y, and z, for example. Okay, so your measurement involve x, y, and z, and it produce a derived quantity called z. Okay, and we seen just now from the Taylor expansion and or the total derivative, we get delta f. Right now I use f. Previously it was delta z. It was delta z. I had it as delta z. Now I call it delta f. Doesn't matter. So that is around x over round f over round x delta x plus let me rewrite it. So round f round x delta x round f over round y delta y plus round f round z delta z. So uncertainty of f, which is our derived quantity, is due to the uncertainty of variable x, variable y, and variable z. And so I can treat a delta f as delta f here, delta x here. So okay, so the sigma, our uncertainty here, okay, when there are x, y, and z independent variable, is delta f square over n. Oh, not big N, not capital N, it is small n. Now what you have to do is you expand the square of delta f here. So if you uh, expand, if you're trying to expand it, it will be long. It will be long. Okay. There's a mistake here. Okay. There's a mistake. This is not just. Okay. Here is not delta x. Okay. This is a mistake. There's supposed to be sigma. Supposed to be sigma x square. Sigma y square. Sigma z square. Sigma z square. Not simply delta. So I intend. I accidentally imitated the approach in number 1 and number 3. So the uncertainty of f is related to the square of round f over round x times the uncertainty of x itself. Okay, so not delta x. Now back to our argument here. Okay, so this one, let's expand this. Okay, so so let's call this sigma, because our function is f. So let's call this uncertainty is as sigma f. So if we square both sides, so sigma x square is the summation of delta f over n. So delta f square. So we can put 1 over n at the outside. So there is round f round x delta x. I want to check. Okay, yes, I use triangle as delta. So let's continue with that. Plus round y, round f round y, theta y plus the round f round z, theta z, and that is to be squared. So there will be 1. There will be 6 term in total. Okay, so 6 term in total. So if we write it, so it is f round x square x square. I'm not showing you the middle of the work here. The middle way, the path that to reach here, because if you expand this and only after you expand and rearrange this, rearrange it, it will look like this. So round f over round x, round f over round y square, y square plus round f z square delta z square plus 2 round f round x round f round z x delta z plus 2 on f round x on f round y delta x delta y plus 2 round f over round y round f over round z delta y delta z. Okay. Now let's bring the 1 over n and summation into the bracket. So there is round f round x square summation of the x square over n plus round f over round y square summation of delta y square n plus round f round z square summation of delta z square. Okay. First three term and then the last three term is plus 2 round f round x round f round z summation of delta x delta z plus 2 round f round x f round y. Oh, I forget 1 over n. 1 over n there. Delta x delta y plus 2 round f round y round f over round z 1 over n summation of delta y delta z. Okay. Okay, now the we can regard this as 0. Z delta x delta y delta z. Those are 0. So those are 0, and then if you look here, that is then the deviation of x. This is standard deviation of no, variance of x. The variance of y. This one is variance of z. So that is partial derivative of x square variance of x plus partial derivative of f with respect to y square variance of y plus round f round z square variance of z. That's it. That is propagation of uncertainty. Okay, so this one here, instead of saying x times z is because it will be 0, it is more accurate if we say summation of multiplication of x and y is equal to 0. So they are they are random and independent, so most likely they will be 0. So we get this propagation of uncertainty equation. So if let's say you have you measure x and y, and then you determine z is x plus y. So x is x. Okay. So you measure x, you get the mean value of x, and with that you get the uncertainty of x, which is that one. And then you measure y, you get the mean value of y, and with that you get the uncertainty of y. So using the simpler the first approach, better with equation number 3 instead of equation number 1 I mentioned just now. Round z over round round z round x delta x plus round z over round y delta y. Okay. So here is a question. Okay. What do you want to use for delta x? What do you want to use for delta y? Okay. So we now we have mm, sigma x as the uncertainty uh, to represent as you have sigma x that represent the uncertainty in x. So you can use theta x here and theta y here. Okay. And if you use the second approach, let me show you here. The second approach here. So delta z is square root of round z over round x square sigma x square plus round z over round y square sigma y square. So that is round x is 1. Okay. Right, so 1 times sigma x plus this here also 1 times sigma y. So sigma x plus sigma y. So what is z? What is z? Z and it uncertainty. Oh, sorry. So z is x plus y. No, x plus y. Mean of x. Sorry. Not capital X. So x y plus sigma plus delta z plus minus delta z. And then this one, delta z is sigma x square plus sigma y square root of that. Okay, so z is x plus y plus delta z. So two different answer. So you will get two different answer. Okay, I think that's all. That is I think this is a lot. This is a lot, but the important is you have to know which approach you are using. Okay. Which approach you are using. So that's all. Thank you.